Hello, my name is Nitin Kanjinadam and I'm going to be presenting on GastroScan, using a convolutional neural network to diagnose gastrointestinal diseases from endoscopy footage. To understand the need for GastroScan, we first need to understand gastrointestinal diseases. Gastrointestinal diseases are any disease that affects the gastrointestinal or GI tract, which is depicted in this image on the right. It goes from the mouth all the way down to the stomach, the liver, and through the intestines out through the rectum and the anus. Unfortunately, 60 to 70 million Americans suffer from gastrointestinal problems, which is approximately 20% of the entire American population. This leads to 250,000 American deaths per year, which, according to the CDC, puts gastrointestinal diseases as the fourth leading cause of death for Americans, behind heart disease, cancer, and COVID-19. Most gastrointestinal diseases cause at least one of three major types of abnormalities along the lining of the GI tract, namely polyps, ulcers, and hemorrhoids. A polyps is an abnormal growth along the lining of the GI tract, which is such as this oval that I'm circling right here in the top image. Next, we have ulcers, which is a sore that develops on the lining of the GI tract. This right here is a stomach ulcer, a sore in the stomach lining. And finally, there are hemorrhoids, which are caused by inflamed or swollen veins near the rectum or anus of an individual. Unfortunately, there are many gastrointestinal conditions that can lead to sickness and death, including but not limited to those listed on this slide. In fact, there are so many gastrointestinal conditions that Dr. S. Guandolini, the founder of the University of Chicago Celiac Disease Center, says, and I quote, "Unfortunately, there are many different gastrointestinal issues, so it is easy to mistakenly neglect them. Some GI problems are mild and usually go away on their own, but some conditions are serious enough that you have to see a physician or gastroenterologist." And this quote just shows the necessity of being able to identify and distinguish between these different gastrointestinal conditions to ensure that each patient gets the care that they need in a timely manner. To diagnose and closely monitor their patient's conditions, doctors will often perform an endoscopy or colonoscopy on their patient. An endoscopy is simply a procedure where an endoscope, which is this long tube with a camera at the end of it, is inserted into the patient's GI tract through their mouth. The only difference between an endoscopy and a colonoscopy is that in a colonoscopy, the endoscope is inserted into the patient through the rectum. Now, this yields a lot of data that the doctor can look through. Many pictures, hours of video footage, and samples that can later be tested in the lab as biopsies. However, even after the procedure is complete, this still takes a lot of time for the doctor. The doctors have to look at all those pictures. They have to review that hours of video footage, and they have to test those biopsies in the lab. However, this is where GastroScan comes in, because GastroScan will significantly reduce the amount of time that doctors have to spend reviewing footage and pictures after an endoscopy or colonoscopy is complete. So first, we need to take a look at the data sets that were used to train the GastroScan models. Namely, there were two, the hypercalvascular dataset and the Cavastir dataset. The hypercalvascular dataset has more than 100,000 images and several hundred videos, while the Cavastir dataset has approximately 8,000 images. When these two datasets are combined and used to train the GastroScan models, GastroScan is able to efficiently and effectively identify abnormalities and diagnose patient conditions. And so here are 5 images from the hypercalvascular dataset that were used to train GastroScan. GastroScan also uses two kinds of models, and a model that aims at simply identifying abnormalities along the GI tract, and another model that aims at actually classifying a condition that a patient may have based on an image of the GI tract. So the abnormality model will classify an image as either healthy, hemorrhoids, or polyps, while the condition model will classify an image as into one of 6 labels: Barrett syndrome, esophagitis, healthy, hemorrhoids, polyps, and ulcerative colitis. These images on the left, there are 6 of them, and each one of them corresponds to a different label that the conditions model will classify an image as. The first models that were used for GastroScan were simply basic neural networks, in which all images were resized to 100 by 100 pixels, and then the data from each of the images and each of the pixels within that image was passed from layer to layer until it got to the end and produced a prediction. This is simply the simplest neural network model, and as a result, it did not yield very great results, having very low accuracy rates. And so After a basic neural network, I created a convolutional neural network, which uses convolutional layers and max pooling layers to also come to a prediction and classify the image. A convolutional layer is shown on the bottom left, and it applies filters to some regions of the image, to compress the image, and it allows the neural network to more easily recognize patterns. On the other hand, a max pooling layer is shown on the bottom right, which further compresses the image and accentuates any apparent patterns in the image so that those patterns can be taken into account when making the final prediction. Unfortunately, the convolutional neural network alone was not enough to generate high accuracy rates within the models because the dataset it was using was very uneven. As you can see on the left, some labels had very few images. For example, hemorrhoids only had 6 images in the dataset, while others, such as the healthy label, had 4,104 images. This caused the convolutional neural network to be very skewed towards classifying images as healthy because that's simply what it was trained on. And so as a result, many diseased images were classified as healthy despite not being healthy at all. And so to fix this problem, I used generative adversarial networks, or GANs, which is when two models are pitted against each other, working against each other. One of them, the discriminator, is trying to classify an image as either real or fake, while the other one, the generator, tries to create images to trick the discriminator into thinking that they're real. And so after running this GAN for around 100 epochs, it begins to generate images that can very easily be mistaken as being real images in the dataset. For example, these two images here are both of esophagitis. One of them is real and the other is a fake that is completely computer generated. And so we can see here that despite one of them being fake and the other being real, they still look pretty similar. And as a result, when the fake images are put into the dataset and used to train the model as well, GastroScan is much more effective and accurate when classifying images of the gastrointestinal tract. Here are the results of GastroScan, which show the model accuracy rates on both training and testing data for each of the 6 models used throughout the duration of this project. The basic neural networks were not the best at classifying the abnormalities and conditions present within an image, being no better than simply taking a random guess as to which label the image fell under. In fact, the basic neural network simply classified every single image as being healthy due to there not being enough complexity within the model to accurately identify the image. The convolutional neural network was slightly better in the case of the abnormality model, and in the case of the condition model, it was significantly better, nearly doubling the accuracy rate from around 16 or 20 to approximately 40%. And finally, a convolutional neural network, when combined with the combined data set of real and generated images, basically an even balanced data set, bumped up the accuracy rate for the abnormality model to around just below 95%, which is much better than simply taking a random guess and will significantly help doctors in the future. As for the condition model, that with a combined data set with a CNN, the accuracy rate was bumped up to around 65%, which although not being the most accurate, is still helpful to doctors and is still nearly 4 times more accurate than simply taking a random guess as to what label an image is. So let's take a look at what we can conclude from these results from GastroScan. We can see that a computer is able to effectively recognize and diagnose gastrointestinal diseases and can be of great use to doctors in the future. A convolutional neural network is particularly effective, especially in the case of the abnormality one that had approximately 95% accuracy. And finally, a balanced dataset is crucial to increasing the accuracy of a GastroScan model. Because without a balanced dataset that has even numbers of images in each label, the model will simply be skewed towards a single label and misclassify many images. And so from all this, we can see that GastroScan will be incredibly effective at helping doctors in the future, reducing both the amount of time they need to spend reviewing footage and images, and also increasing the quality of care that patients receive. To allow users and doctors to easily use GastroScan, I also created a simple website. The website consists of three main parts: the React.js frontend, the Express.js backend, and the model hosting using Flask. So once a user uploads an image to the React.js frontend, the frontend will send that user's image data to the backend, which will then send it to the model to be classified. Once the model classifies the image using the models that were trained earlier, the Flask backend will then send the prediction to the Express.js backend, which will then send it to the frontend where it will be displayed to the user. Now, here is a demonstration of that website in action. Here is the basic GastroScan website. Currently, I'm using the abnormality model. So if I were to go to choose a file and then choose a healthy image and upload that file to the website, you'll see that the website classifies it as healthy and displays it to the user. Currently, the website is still very rudimentary, but you can see that it does in fact work and display the proper label to the user. If I were to go back and use the condition model instead, and instead say choose a image with Barrett syndrome, and instead upload that to the website, it will classify as having Barrett syndrome and give it a red to indicate that the patient is not healthy. Again, I can go back and continue to upload images in the future. However, just because the GastroScan website works does not mean that the work is over. In the future, I hope to implement many new features in GastroScan. First of all, I hope to gain access to larger and more comprehensive datasets that have more labels and more images per label to allow GastroScan to analyze and diagnose a greater variety of gastrointestinal conditions. In addition, I hope to try new types of neural network models to classify the images, such as a graph neural network, which may even be better at classification than a convolutional neural network. Moving over to the website, I would like to change the website to allow users to upload video files for classification, and then have GastroScan analyze the video and tell the user which sections of the video warrant further review by a doctor. And finally, for the website, I hope to add an account system to the website that allows users, namely doctors, to manage their patients and their images, videos, so that they are able to keep track of what image and video corresponds with what patient. Thank you for watching and have a great day.